Welcome to another video example. Today we're going to look at a second example of solving a linear system. This is going to be a little different than last time, so let's take a look. Here's a nice system, and this one is a little bit special. If you notice, we have all zeros on the right-hand side. That situation has a name. It's called a homogeneous system. So let me just sort of write this down here. That's called homogeneous, or homogeneous if you like. And one feature of this system is that it always has what's called the trivial solution. So the trivial solution in this case is the vector x1, x2, x3 equal to the 0 vector. So 0, 0, 0. So you can kind of see that by inspection, if all these x's, x1s, x2s, and x3s were 0, you'd of course have 0 on the left-hand side. And because this is the homogeneous system, we have zeros on the right-hand side. So that's always a solution. Now, is it the only solution? So that would be the key. So let's take a look. In order to determine if it is the only solution, we really have to go and solve it. So let's do our usual trick and convert this into the augmented matrix. So if you remember, we can take the situation and write it without the variables, and we'll just keep track of the coefficients. So here we'll have the matrix of coefficients on the left-hand side. So let's write these down here. -1, and then we have a little dotted line, and on the right hand side we always put the numbers we find on the right hand side of the equal sign, and here this is very easy, they're all zeros. Okay, so there's our matrix, and we're going to do row operations on it again and get it into a nice form, and we'll see what kind of solution we've got. So let's take a look at how that's going to work. I think the first thing I'd like to do here, and remember what our goal is always to convert this into something that nicely corresponds to zeros below the diagonal if we can, and then we'll see if we can eliminate everything above the diagonal and then easily figure out what the solutions were. Okay, so as a first step, I think it would be good to take this first row and divide by 3. And the reason for that is then I'll have 1s everywhere, and then it'll be easy to multiply by the correct thing to perform row operations. So first thing I'm going to do is I'm going to take 1/3 times row 1, create a new row 1. Okay, and then I will, but before I do that, I can also see that it'd be nice to just take -1 times this row 1 and add it to this row down here. So I'm going to take minus old row 1, add it to row 3, and make that a new row 3. We won't do anything with row 2 just yet. Okay, so if we do that, let me do this bottom row first because it's easy to see. So -3 times this 3, that gives me a 0 here. I have a -1 times this -3, that gives me +3, plus the -5 is -2. And then -1 times this 3 gives me -3, plus -1 is -4. Okay. The nice thing about having the zeros over here is that these row operations will never change them to anything except what they started with, so we'll always have zeros here. I didn't do anything to the second row, so I'm going to keep that the same. And then I took this first row and I divided by 3, so that gives me this. Okay, now that's much easier to deal with, and it's easy to see what's going to happen in the next stage. So what I'm simply going to do is I'm going to multiply by -2 times row 1 and add it to row 2. So let's go ahead and do that. Well, I think we better do this on the next sheet because we filled up this one. Okay. All right, so here we are. We have our matrix rewritten here, and we're going to do some more row operations on it. So just as I mentioned before, the next thing it seems reasonable to do is take 2, or -2 times this first row, and add it to row 2. So -2 times row 1 plus row 2 will create a new row 2. And I'll just put the result down here. Nothing happens up here. So the nice thing here with the homogeneous system is that we always get the same zeros over here. So it's less to keep track of in a way. Alrighty, so I do -2 times this and add it to that. That zeroes out this 2. minus 2 times this and added to minus 1. So that becomes positive 2 added to minus 1. So positive 2 added to minus 1 is just 1. And now over here I have minus 2 times this added to 4, and that gives me positive 2. And then down here we still have our same old thing. We haven't done anything to that. All right. Now, what we should do next is, it looks to me like a good idea is to take 2 times the second row and add it to the third row to create a new third row. And when we do that, we see something different. So let's see. Nothing happens up here. Because it's a homogeneous system, nothing happens to the right-hand side. And I'll just leave this the same. But when I add 2 times row 2 to row 3, this becomes a positive 2 added to the negative 2 gives me 0. I have 2 times 2, which is 4, added to minus 4, which is 0. And now we see something new. We see this row of zeros down here, and that will give us something that we haven't seen before. At this point, I'm kind of, there's not a whole lot left to do. We can do a little bit. I can try and eliminate some things above the diagonal, but I'm really done below the diagonal, and this 0 here, that kind of prevents me from doing things. I'm not going to be able to zero out these positions because I don't have anything to do it with. What I can do is I can get rid of this minus 1 here by taking row 2 and adding it back to row 1. So let's just go ahead and do that and see what happens. Row 2 added to row 1 gives me a new row 1. And I'll soon run out of things to do. So nothing can ever change this row of zeros down here. It's no multiples of anything can help. Let's see. So this stays a 1 and a 2. I add these rows together and I get a 0 here. I'll get a 3 over here and I'll get a 0. And at this point, there's nothing left to do. What I do at this point is I'll have to convert this back into a system of equations and see what they imply. Okay, so let's go and do that. Whoops. Didn't mean to do that. So here's my system again, and now I'm going to convert it back into equations. Okay, so this first equation over here, 1, 0, 3 with a 0 on the other side, that corresponds to the equation x1 plus 3x3 equals 0. Okay. So what does that tell me? Well, it gives me a relationship between x1 and x3. I also know here from the second row that I have x2 plus 2x3 is equal to 0. Okay. So as I mentioned in class, what we do in a situation like this is these diagonal entries here, these are pivots. They correspond to what we call the leading variables. This is in the x1 column, so x1 is a leading variable. Here, this one over here is in the x2 column. x2 is a leading variable. There isn't anything down here. It's just a 0, so there is no leading variable for x3. And in fact, x3 is not a leading variable. It is a free variable. So if I solve these equations, what we usually do is we solve for the leading variables, and I see that x1 is equal to minus 3x3. And I see that x2 is minus 2x3. So what that tells me is my solution, which I normally think of as the vector x1, x2, x3, I can make some substitutions in there because I know that x1 is always equal to minus 3x3. So I'm just going to write that there, minus 3x3. Similarly, x2 is equal to minus 2x3. And x3, well, x3 is just itself. Now if you look at this, you realize you can factor out an x3, and we're left with x3 scalar times this vector here. Okay, and that in fact gives me the solution set. So in this case, the solution set is the following. It's a set of vectors, x1, x2, x3, that are equal to a constant multiple. We can write that as a c or an x3 or whatever, times this vector, minus 3, minus 3, minus 2, 1. And C here is free. It's allowed to be any real number. Okay, so what this means is that I have an infinite number of choices for C. And so the solution set has an infinite number of points in it. It's every scale multiple of this vector here, minus 3, minus 2, minus 1. And so this is a case where we have an infinite solution set. And this is how I'd write it. All right. Next, we're going to look at a slightly different situation, but I think we'll take a little break before we do that. And we'll go back to the beginning and see what happens.